Alright, what's up, Logic fans? It's Ash coming to you with another one here, 6.1, our introduction to Chapter 6, Quantificational Syntax. Here we're going to learn about how our new sentences, quantificational sentences, can be used in conjunction with our old rules like modus ponens and modus tollens and De Morgan's and commutation and so on and so forth. Alright, let's rock. Okay, so the whole point of 6.1 here is to show you that we can actually use all of our old rules, modus ponens, modus tollens, De Morgan's, and so on, in quantificational contexts. So we can look at certain sentences involving the quantifiers, involving property constants, relations, identity, and so on, and we can still apply all of our old rules. We will have occasion to introduce new rules, and they will be necessary. But right here, it's important to just sort of get a feel for how the old rules work with our new quantificational sentences as defined very sharply in Chapter 4. So, first thing we want to do here is go over an official definition of a quantificational deduction. This definition is just like the definition of a propositional deduction from Chapter 3. The only real difference is that we're now working with sentences with quantifiers as opposed to sentences that are propositions as they were rigorously defined in Chapter 1. So let's take a look at this. A quantificational deduction, and we'll see an example in just a second, is an m×2 grid where every quadrant in the left column contains exactly one quantificational sentence, and every quadrant in the right column indicates whether the sentence to its left is a premise, an axiom, or follows from one or more previous sentences by a syntactic rule. Again, I'll give you a concrete example of that in just a second, but it's just like what you remember from Chapter 3. Furthermore, we say that an argument is the same as ever, right? It's a set of sentences, okay? This time a set of sentences with quantifiers and quantifier apparatus, the stuff from Chapter 4. Alright, so a quantificational argument is syntactically valid if and only if there exists a quantificational deduction of its conclusion from its premises. So let's go ahead and take a look at an example. Okay, so here we have an example. We've got an argument here. It's valid, and your object is to show that it's syntactically valid. Notice it's a quantificational style sentence as defined in Chapter 4. So, you've got FA or not FB, that's a premise. Not FB, that's a premise. And the conclusion is that FA is true. So, you have to show that it's syntactically valid, and in order to show that it's syntactically valid, you have to produce a quantificational deduction of it. So without my showing you, go ahead and see if you can't figure out how to show that this argument here is syntactically valid, okay, based on the definition. And yeah, just pause now and give that a shot. Okay, hopefully you were able to make some progress. If not, here's a bit of a hint for you. So you're going to have an m×2 quadrant, all right? So there's going to be m lines going down and two columns across, okay? And you're going to have your premises arranged at the top as per usual. By convention, we put all the premises up there. And then, you've got to get new lines until you get FA, and you're going to apply our old rules, modus ponens, and so on and so forth, in order to achieve it. So pause now and see if you can't finish it and produce the syntactic deduction. Okay, hopefully you were able to get it, right? It was pretty straightforward. So you need to flip around the sides here, and then you've got the negation of not FB in line 2, and so disjunctive syllogism applies, and you've got it. And what do you have here? You have an m×2 grid, right? In this case, it's got 4 lines. Well, I have this blank one here just for readability, but you've got these 4 lines, a 4×2 grid. Each line is a premise or follows from one or more previous lines by one of our syntactic rules, and the last line is the conclusion. So this is indeed a syntactically valid argument, and this syntactic deduction proves that it is a syntactically valid argument. Okay, let's try another one just so you're getting familiar with how these old rules work with the quantifier sentences. Okay, so in this case we've got an argument. You're supposed to show that it's syntactically valid by producing a quantificational deduction, and you've got two premises here and a conclusion, and I've got the two premises here started for you. So pause now and see if you can't figure out, using our old rules, how to deduce the conclusion from these premises and show that this argument is in fact syntactically valid. Pause now. Okay, hopefully you were able to get it, but again, not too hard, right? We just double negate this, right? And then we've got the result right here from double negating 2, and then we've got a modus ponens, right? So notice that 1 here is not an existentially quantified sentence. It is a conditional whose antecedent is an existentially quantified sentence and whose consequent is an existentially quantified sentence. So modus ponens does apply, right? If P then Q, P therefore Q. So in this case, this whole thing here is P and this whole thing here is Q. Now, if the existential quantifier had ranged over this whole thing so that the sentence was an existentially quantified sentence and not a conditional, then modus ponens could not be applied. Okay, so picking up on that theme of when you cannot apply one of our rules of inference, right? Rules of inference, the form of the rule, like modus ponens, has to be followed precisely. So let's look at a case where it fails for a second, and we'll just go ahead and do this one out together. So suppose your test was showing that this is syntactically valid. Now here's a clue. It cannot be done because this argument is not syntactically valid. Okay? It's just not. But let's suppose that you were trying to prove it to be so. All right? You might start off with your two premises, just like so. Sorry, let me delete these from the last one. And then you might go along as follows. You might say, okay, I'll just go ahead and conclude for all y, gy based on disjunctive syllogism on 1 and 2 and QED. Look at that, syntactic deduction. Wrong. This is an incorrect use of disjunctive syllogism. Disjunctive syllogism applies to disjunctions. 1 here is not a disjunction. It is a universally quantified sentence. Okay, so just like in the last one where we actually had a conditional, but you could imagine there being actually an existentially quantified sentence instead of a conditional, right? You cannot apply it if it's the existentially quantified sentence. You cannot apply it if it's the universal sentence. You can only apply disjunctive syllogism if the sentence in question is actually a disjunction. You can only apply modus ponens and modus tollens if the sentence in question is a conditional, and so on. So this is incorrect, okay? This is not deducible. And notice, okay, that we can prove that this argument is not valid semantically by producing an interpretation, right? So on this interpretation, you've got two objects. The first one has F and lacks G. The second one lacks F but has G. And so it's true that everything in this domain is either F or G. It's also true that not everything in the domain is F. For example, B is not. But does it thereby follow that everything in the domain is G? No, right? So true premises, false conclusion, and so we can see that this is in fact not a valid argument, and therefore it should not be syntactically deducible. You should not be able to produce a quantificational deduction of it, and indeed you can't, and when you think you can, typically some mistake like this is made, like you applied disjunctive syllogism when it was illegitimate to do so because you applied it to a universally quantified sentence and not a disjunction. So let's look at another example, but this time I want to emphasize that in addition to the old rules being available, modus ponens, De Morgan's, and so on, and we're going to look at others, your axioms are available. So you can use LEM and LNC to invoke quantificational sentences if you like, and you can do that in this one. So go ahead and show that this is a syntactically valid argument by producing a quantificational deduction of the conclusion from the one premise, and your hint is that you may need to use one of your axioms in order to do it. So pause now and give it a try. Okay, I'm going to give you a hint now. Hopefully you've had a chance to work on it, but here's a couple of lines filled in. So what we are given as the premise is a biconditional. So we just broke it apart into two conditionals here in line 2. And then what I did was I simped out the left part. We won't be needing the right part. We simp out the left part here, and you can deduce the conclusion here in 2 steps from this. Your hint is that you need to use one of your axioms. Okay, so pause now and see if you can finish it. All right, hopefully you got it, but yeah, I mean in 3 here what we have is this thing here, this universally quantified sentence logically implies this thing here. The problem is that this thing here is a contradiction. This is of the form P and not P, okay, and recognizing that is the key. So then you invoke LNC and say, well, it's not the case that P and not P, which sets up a really nice modus tollens. Notice sentence 3 here is a conditional and not a universally quantified sentence, so it applies and you get the conclusion as desired. All right. Okay, let's try one where instead of using rules of inference like modus tollens and modus ponens, we're using rules of replacement like De Morgan's and so on, okay, and distribution and impla and things like this, things that allow us to go inside of even a universally or existentially quantified sentence and play around with what's going on inside of it. So in this particular case, see if you can't deduce this conclusion and prove that this argument is syntactically valid, right, from this premise here. And I'll just give you a second to pause now and try that. Okay, so here's your hint. You're given this one thing to work with, and it looks like it's a De Morgan's, right? You have a negation outside of a conjunction, and we can use this, even though this is an existentially quantified. De Morgan's is a rule of replacement, so we can go inside the nature of the sentence and play with it. And so from 1 we get 2 here, and then how did I get from 2 to 3? How did I finish that off? That's right, that was com, which is also a rule of replacement, com on 2. We use that, and then how do you get the conclusion from that? So pause now and see if you can get the conclusion. Okay, hopefully you were able to get it, but the conclusion was just arrived at from 3 to 4 by way of impla, also a rule of replacement, and that's how those kinds of things work, okay? And so we've got a quantificational deduction of this conclusion from the premise, and therefore this is a syntactically valid argument per our definitions. Let's see if we can squeeze in one more. Go ahead and give this one a shot. From 1, deduce 2 syntactically, please, and you're going to have to call all your tricks, okay? Here's your hint. Notice the negation here. Notice the negation here. Pause now and see if you can't do this one. Okay, so the key here is to realize that you've got a disjunction and both disjuncts are negated, and so you can apply De Morgan's to get the negation on the outside and turn it into a conjunction, and after that it's just a matter of adding the not case. So again, you get the 2 negations and can apply De Morgan's yet again, and then you just apply as necessary here. And whoops, I've added an extra line there. I apologize. So it should look just like that. Okay? Plenty of practice problems in the text. Keep doing them, right? Old rules applied to new sentences. You need to understand how that's done, what can be done, and what cannot be done. So just work on those texts, and we'll see you on the next video, Logic fans.